If you watched the videos last night, you heard Mr. Fullerton talk about conservative forces. This is going to be a mini lesson. I'm just going to give a short lesson to maybe clear up some confusion that you might have had with those videos and to elaborate on some things I think Mr. Fullerton just kind of glanced over pretty quickly. So first of all, conservative forces are a very important concept. Conservative forces, it has nothing to do with politics. It's not like the it's not the opposite of liberal forces. No, it's conservative forces have to do with conservation laws. Whether a force is conservative as it acts on an object and does work on an object or system gives rise to whether energy is going to be conserved in that system, energy or momentum or things like this. And so the main point, he gave 3 different definitions of conservative forces. The main point is that if a force is conservative, then the work that it does on an object or a system of objects is independent of the path that the object takes through space. So I've set up a little demonstration here to kind of show you, give a visual for that. I have 2 masses, let's say they're stars, and then I have 2, let's say they're asteroids. They're both starting from the same location, and if you notice, they have to start with the same velocity, 2.33 meters per second. Both of them start with the same velocity. One is pointed this way, though, and one is pointed that way. Now, if the forces exerted on those 2 objects by these 2 large objects are conservative, then line integral, right? You have the force and the infinitesimal displacements, and the angle between them constantly changes. The force constantly changes. So if you want to know the work done on a very complicated path like this, you'd have to do some pretty sophisticated mathematics. And really, with 2 masses exerting gravitational forces, you'd probably want to use a computer to do that. But anyway, so remember, they started with the same energy. They started with the same kinetic energy, and it looks like right about there is where they both were at the same location. So at this point,
Oh, I remember this from last year.
yeah, I think I talked about it a little bit last year. But it's going to be a lot more important this year because of some of the, especially in second semester, when we talk about things like electric potential and electric fields, we actually use dot products with electric fields to define things like voltage or electric potential. And that only works if we're dealing with conservative forces. It only works if we're dealing with conservative forces. So it's real important, a lot more important in physics C than it is in physics 1. So we know that the velocity of this object, the one that's at this location now, is 1.15 meters per second. So if I rewind this and run the simulation again, when the other object reaches that point, it should have that same velocity. Oh wait, I'm looking at the other one. Right about there, pretty close. 1.16 meters per second, right? Essentially the same thing. I probably didn't stop exactly at that point. So it didn't matter that it took this guy longer to get there. It didn't matter that he took a very, very different path through space. That doesn't matter. All that matters is where they started and where they ended. Okay? If the force is conservative, then the work that it does on objects as they move through space is independent of the path actually taken through that space. For this reason, exactly 365.24, or however many it is, days from now, once the Earth gets back to its location that is at right now, its energy will not have changed because the path that it takes, if it starts at a location and ends up at the same location with the same energy, then the total work done on it will be 0, right? Even though, yes, the sun does a little bit of work on the Earth when it gets closer to the sun in its elliptical orbit, and then it does negative work when the Earth moves away from the sun a little bit in its elliptical orbit. By the time it gets back to its starting position, then its energy will be exactly the same because I should have started with one of the other definitions of work done by a conservative force, or one of the other definitions of conservative force is that the work done on an object as it moves through a closed loop, meaning it gets back to where it started from, And it doesn't need to be a circular loop. It just needs to be an object going somewhere else and then coming back to its original location. Only under the influence of a conservative force, the total work being done will be zero. I mean, you can think that if you move away from this guy, negative work is being done by the gravitational force, and then positive work is being done by the gravitational force. Why is that? Well, there's a gravitational force pointing this way, and going this way, the displacements, if I call that delta R, would be 180 degrees. So the work done is F times delta R times the cosine of 180 degrees, which is negative. Cosine of 180 is -1. Conversely, if it moves back this way, then it's going to be positive because the angle is now 0 degrees. So the cosine of the angle between those two is going to be 0 degrees. Okay. Note that this won't be good enough because delta R, the force actually changes as you move closer and farther away from a large planet, right? If we're talking gravitational forces on the large scale, that force actually changes. So you would actually have to do a bunch of little tiny dot products of whatever the force is at that location, dotted with the infinitesimal displacement dr over that interval. And then you'd have to actually do the integral where you'd have to define that force as a function. Okay, and we'll talk about that now. And I did make this other one, but I don't want to take up too much more time, but I threw another object in here. Made it again. So if y'all want to see after you guys get going, you know, I have 3 objects now, all started with the same energy, the same kinetic energy, or the same velocity. So at this intersection, these 2 objects had the same speed. At this intersection, these 2 objects have the same speed, and these 2 actually cross down here a little later on. They have the same speed there. Again, the work done on these 2 objects as they move from the same starting point to this location here, the work done is independent of the path that they take, right? It only depends on where they start and where they end up. They will lose or gain the same amount of energy regardless. That is only for conservative forces. Okay, it doesn't work for forces like friction, forces like air resistance, because those are dependent on the direction of motion or the path that the objects take. Okay, I think one of these guys ends up, or 2 of these guys end up orbiting. You have binary star systems where planets will actually orbit both stars. Star Wars, if you ever watched the original Star Wars, that guy crashed into the sun. But these 2 actually orbit highly eccentric elliptical orbits, but they actually orbit. Okay. So since we're talking about gravity, and just so you know, later this year, at the end of this semester actually, we will do a little mini unit on gravity that will be quite a bit more robust than what we did in AP Physics 1. And that's kind of what I want to talk about now, because in Dan Fullerton's video, he did talk about the gravitational force, Newton's law of universal gravitation, but he wrote it differently. And I want you guys to understand why. So we learned last year, right, Connor? We learned last year that if I have 2 masses separated by a distance, and last year I called this distance r, and you might have wondered why you call a distance r. We learned that the force of gravity between these 2 objects is big G times m1, m2 divided by r squared. This is the little kid definition of Newton's law of universal gravitation. This is the little kid version. Okay. Why is this r? We know at this point that r is what we call the general position vector. Okay. So the big kid definition of Newton's law of universal gravitation has to, first of all, you have to choose your coordinate system. So I'm going to choose the origin of my coordinate system here at the center of M1, and then I'm going to indicate the position of M2 in that coordinate system by drawing a position vector, which I then label R. And then if we know that the force that's acting on M1 or on M2 actually points this way. That's the gravitational force that acts on M2. If R is positive, then the force of gravity on M2 must be negative because it points in the other direction. So that's why there's the negative symbol in front of it. And then you might have noticed that Mr. Fullerton puts a little r hat next to it. Well, r hat is simply the unit vector in line with R, in line with the displacement vector R, a position vector R, sorry, that has a length of 1 unit. So multiplying this quantity by R hat doesn't change its size. It just tells you the actual direction. Okay. R hat points this way, negative. This value times R hat is a vector. This vector actually that points in the opposite direction. Okay. So this is actually the big kid definition of Newton's law of universal gravitation. And yes, that's the version that Newton used himself. Okay. That makes sense? So in case when you were watching the video, Alex, when you were watching the videos last night, in case you were confused as to why that he was saying that, this is why. Because we all saw this last year, but in just the normal algebra version. We didn't talk about it. It was like, what's the magnitude of the gravitational force? Those are the questions we had last time. All right. Mr. Fullerton also talked about that the work done by a conservative force, and again, this only works if we're talking about conservative forces, is equal to the negative change in potential energy. Okay. Now, this could be change in electrical potential energy, it could be change in gravitational potential energy. Okay. Second semester, we'll actually talk about this in terms of the changes in electrical potential energy, because the electric force is also a conservative force. The gravitational force is also a conservative force. When we did energy conservation last year, we talked about like roller coaster physics and stuff where things change elevation and velocity simultaneously, but the energy was conserved. The mechanical energy was conserved, meaning kinetic and potential energy. But we always neglected friction, right? Unless we were doing the work done by friction as well. But friction is not a conservative force, so this won't be true for friction forces. So you got to be more methodical when you deal with those. But this comes from the definition of work. This equation can be derived from that, but just why is it negative? I remember that confusing me, so let me just tell you why it's negative. Let's say an object falls from here to here. Say this is the initial position, this is the final position. You saw when you watched the videos last night that the gravitational potential energy for an object, say above ground level, is mg times the height above the ground level. And so a change in gravitational potential energy due to the work done by the conservative gravitational force is going to be mg times the ending height, mgy, minus mgy naught, which is negative, right? The potential energy here is less than it was here. So the work done by the conservative gravitational force is equal to the negative change in potential energy. Conversely, if this was my starting point and I throw an object up into the air, we should know at this point that the work done by gravity will be negative because of moving up, displacement up, gravitational force down, 180-degree angle between them. So the force times the displacement times the cosine of the angle between them will be negative. This will just be mg times final position, mgy, minus mg times initial position. And so that ends up being positive, right? And so the work done by the conservative force in that case would end up being, as it moves up, I think I jumped a step last time, I'm sorry. This ends up being positive, but because of this negative here, the work done by gravity will be negative, right? We have a positive change in potential energy, so the work done by the gravitational force will actually end up being negative because it's moving. It's moving away. Its displacement is in the opposite direction as the force. So that's if you ever wonder why that negative is there, because negatives, especially when we start talking about electricity, electric forces, and voltages, electric potentials, negatives trip people up so much. Tripped me up when I was learning about this. There are some problems that to this day will still trip me up, and I'll have to solve them 2 or 3 times before I'm comfortable actually solving them in front of a class. But the negatives are really tricky. So understand, if you ever wonder why the work done by conservative force is the negative change in potential energy, just think about this. Just think about as objects move up, delta U is positive, right? But we know if they're moving up, the gravitational force points down, the work done by the gravitational force is negative. meaning it takes energy away. That's another way. Negative work is being done, the object is losing energy. Objects lose energy as they move up. They gain energy as they go down. When they're moving down, delta U is negative, so the negative times the negative delta U is positive. Gravitational force does positive work as the object falls down. Okay, for this definition, because this was on the video too, so I want to make sure we talk about it a little bit, we're going to hit this a lot harder at the end of the semester. This height is a height above some arbitrary reference point. Okay, when we talked about gravitational potential energy last year, we just talked about, well, we got to pick a height, right? I can say that the gravitational potential energy of this guy above the counter is different than the gravitational potential energy of this guy relative to the floor. I'm talking about a marker on the video. And so it's arbitrary. Your reference point is arbitrary. You can use conservation of energy to say how fast this guy's going to be going at countertop height or how fast he's going to be going at ground height. So this is a measured height relative to some arbitrary reference point. When you're out in space, you can't just use some arbitrary reference point. Okay? So we need to be a little more robust. We need to be a little more rigorous in our treatment of potential energy on the large scale. We actually want a reference point that is common to every point in the universe. And you might say, well, how is that even possible? Technically, it's not possible, but mathematically it is. What point in the universe is equidistant from every object in the universe?
You.
What?
You. You're in space.
What did you say? Oh, no, you're 0 meters away from the Earth, but you're very many meters away from the sun, and even more away from another galaxy. There is no center of the universe.
The edge of the universe?
There's no edge of the universe.
Infinitely far away.
Infinitely far away. That's the only reference point that is equidistant from every point in the universe. Again, technically it's not possible. Mathematically it is. Mathematically we deal with infinities all the time. If you're in calculus, you know that, right? Or if you've taken calculus, you know that. So that's why when Mr. Fullerton essentially used this expression to derive the formula for gravitational potential energy, the actual formula for gravitational potential energy, first what he did, he solved this for delta U, and he said the delta U is going to be equal to the negative, and this is now change in gravitational potential energy. We're talking gravitational potential energy, is going to be the negative work done by the conservative gravitational force. Well, we have a formula for the work done by any force. That's going to be, and the negative is still there though, that's going to be the integral of the gravitational force dotted with dr. Okay. But what we're going to do, we're going to say, let's say we want to know the value of the gravitational potential energy of an object here. What we're going to do is we're going to take an object from infinitely far away, and we're going to imagine the gravitational force doing work on it as it moves from infinitely far away to that location. And we define gravitational potential energy in that way. Okay. So we're actually going to do this integral from infinity to whatever arbitrary position we happen to choose, and we call that R.
Arbitrary.
Physics jokes. So why infinity? That is literally the only mathematical place in the universe where we can measure all gravitational potential energies from that reference point, a common reference point. Okay. And then what I like to do, and Mr. Fullerton didn't do this, he just jumped straight into it. I like going to the side and saying, and this is especially true when we get to electricity. This is a preview of the level of mathematics we'll have to be dealing with when we get to electricity. We'll actually learn that the definition of potential difference or voltage difference between 2 points is going to be the negative integral of the electric field dotted with dr. So it's a very similar process that we use when we define electric potential. And so I like say dealing with the dot product first. Force of gravity dotted with dr. Notice that what I said, we took the object from infinity from way over there at infinity, and we had it move this way, gravitational force constantly changing, right? But we moved it this way with an infinite amount of little tiny displacement drs. And as it was just being displaced dr, it had a force acting on it, the force of gravity acting on it, which was doing work, right, as the object moved this way. And so F dot dr is going to be, again, it's a scalar now when we do the dot product. It's going to be the gravitational force times dr times the cosine of the angle between them. And this is where the conservative force concept comes in and might start giving you a headache because this is pretty complicated stuff. But because it's path independent, we could have, and make the math a lot more difficult, we could have taken that mass from infinitely far away and did the zigzag pattern and went around this way and went around the planet and went back here and then ended up here. But because the gravitational force is conservative, the amount of work done in doing that would be the same amount of work that would happen if I took it from infinitely far away and just brought it straight in, where the cosine of the angle between them would still be the cosine of 0 degrees. So it would be 1, right? That being said, this is just going to be Fg times dr, because the cosine of theta is literally 1, right? So when I have an integral that looks like this, before I even start evaluating the integral, I like saying, okay, what's the dot product? Sometimes the angle is not 0. Sometimes the angle isn't 180. Sometimes there is an angle between them. If it's a conservative force, though, you can just say, well, the angle's 0, right? Angle 0. Or it's going to be 180, right? But in this case, it's 0 because the object is moving from infinity to this location, not from this location to infinity. If it was that way, then my drs would be in the opposite direction, and the cosine of the angle between them would be negative 1. Okay. So once I know what the dot product is, it is a scalar, it's just FGdr, then I can say, all right, well, this is just the integral from infinity to position r of the gravitational force times dr. Seems, who's paying attention? Who was that? Was that Alex? The guy that didn't watch the videos? And then I have an expression for the gravitational force, right? I have an expression for the gravitational force. It's going to be the negative integral from infinity to r of negative big G times m1, m2 over r squared times dr, right?
So dr is basically just r hat.
No, oh, r hat we're leaving off because technically it's, oh man, I'm sorry. Technically Fg dot dr, this is a good point. This is a good thing you brought this up. Is big G m1, m2 over r squared times r hat dot
It's no longer
dr.
Okay, that's what I thought.
Yeah.
it's scalar, so it doesn't need to.
Yeah, but that's correct. Technically, you're not dotting this with dr, you're dotting r hat with dr, where this is just the magnitude of the vector. Yes, sir.
On 1 and 2, would I be able to just say also equal to the positive integral of r to infinity?
You could, but you'll see that our answer is here is actually going to be negative, right? Because when you do this integral, you're going to end up with a negative, right? So you could do that if you know where you're going.
I just plug everything into the calculator.
You're going to have calculus classes in college if it's like the ones that I took, where you're going to have tests where you don't get to use a calculator.
Oh yeah.
So be ready for that. Yeah, so you're used to it. All right, so finishing this off, I have the negative. First of all, G, M1, M2 are all constants, right? So I can bring those out, negative G, M1, M2. I can actually bring the negative out too to just make it positive. So it'll be the integral from infinity to r of r to the negative second times dr, right? And so that's going to be big G times M1 times M2. The integral of r to the negative 2 is R to the -1 over -1, right? I add 1 to the exponent, and I divide by that same thing. And I evaluate that from infinity to R. I don't know why I put this down here. I'm sorry. I'm going all over the place today.
So in this case, R would be a vector then, right?
No, our result here is not a vector.
Oh, okay.
The dot product of the R hat and dr vectors is actually a scalar. And so now I have big G times M1, M2. And you can rewrite this if you want. This is essentially -1 over R, but I evaluate that from infinity to R, which is equal to big G times M1, M2 times evaluated at the top limit, -1 over R, minus evaluated at the bottom limit, -1 over infinity. Yes, technically you're not dividing by infinity. You're dividing by a number that approaches infinity. So I don't want to get you in trouble in your calculus class, but from a physics perspective, you can just call 1 over infinity what number? 0. Yep.
Why is that -1 over R?
It's always minus, but then the expression is -1 over R. And so this just approaches 0. It's close enough to 0 that we can call it 0 in physics. And so this is just going to be negative big G M1, M2 over R. And that is
You just got rid of a square.
the change in gravitational potential energy.
I hate this so much.
Welcome to physics. This is all you get.
Yeah. And notice that when I start, what do you think our potential energy at infinity is? Yep.
G.
If I put infinity for R, what's our potential energy?
0.
It's 0, right? This is where our knowledge of potential energy last year clashes with the real nature of potential energy, gravitational potential energy. Because if our initial potential energy at infinity is 0, then we don't need the delta, because final minus initial is just final potential energy. Meaning that the potential energy at every location, the gravitational potential energy at every location in physical space is actually negative, okay? And as the object gets closer and closer, it just gets less and less negative, okay? As R gets smaller, the potential energy goes up, but it goes up in the negative direction, okay? I'm not going to elaborate too much on that now. We're gonna hit that point again a lot harder when we get to the end of this semester, when we do gravity as its own little mini unit, okay? But I just wanted to show you how you can use stuff that we used last year. You can treat it at a higher level using the integral definition of work. And yeah, it is a scalar. It is a scalar because energy is a scalar, okay? For the same reason, I'm not going to go into it, for the same reason in Hooke's law, when you do the integral, the work done by an ideal spring, which the ideal spring force is a conservative force. In reality, it's not going to be, because there's internal energy changes that happen when a spring gets compressed or stretched. But an ideal spring actually will do conservative work. It will act as a conservative force. And so if you take Hooke's law, which is spring force is the negative K times displacement X. Right, this is the big kid definition. Last year we kind of leave off the negative because we just say, well, what's the spring force? If you displace it this way, it points that way. If you displace it this way, it points that way. Like if I stretch a spring, the force is in the opposite direction of the stretch. If I compress a spring, the force is in the opposite direction. That's where this negative comes in. But if I want to figure out how much work is done compressing a spring, then you just do the integral of this dotted with dr, or dx if it's in the x direction, or dy if it's in the y direction. But note that if you're doing work by pushing, what can you say about the nature that the spring force, the work done by the spring force is? Well, yeah, it's going to be negative. If you do positive work compressing a spring, we'll look at that same work from the perspective of the spring, it'll actually be doing negative work because it's pushing this way as the force is going this way. Why is that important? Because if you're dealing with conservative forces, this works. So you could be doing a different amount of work. You could be doing a different amount of work. There's definitely, because your muscles actually contract and flex, and you do a lot more biological work than the work when I lift this weight. When I lift this weight, if I give it 10 joules of potential energy, I'm probably doing more than 10 joules of work because there's a lot of internal stuff going on in my body, right? In addition to moving the weight, I'm moving my arm. I'm moving the muscles. The muscle fibers themselves are constantly flexing and unflexing. And so there's more work being done there. So if I want to know about the change in energy of the weight, I don't think about the amount of work that I actually do, the total amount of work. I think about the work that is being done by the conservative force, which is gravity. That's much more robust. It's much more general, right? And we want generalities in physics because they're more useful. That's why the general theory of relativity came along after the special theory, because it took a lot of time to generalize everything. Okay. All right. One other thing I want to talk about, and then you can get started on this. Watch the conservation of energy. That was the second video. This is just detailing some items from the first video. But yes, do that. Just one thing though I want to point out is that the force, the magnitude of any conservative force, there's another way to calculate it. If you have the potential energy function, that is a, what am I trying to say? That is related to that conservative force. Here I have a potential energy function that is related to the gravitational force, right? So if I want to calculate the force, if I have the potential energy function, all I have to do is do the negative derivative of that potential energy function with respect to not time, but with respect to position. Mr. Fullerton says du dl, but dl is just another way of writing an infinitesimally small displacement. So I'm going to use dr. This is needed on every AP Physics C exam. It will be on either the mechanics or the E&M exam. They'll give you a potential energy function, and you'll have to do something about finding the force. This is not on your formula sheet. Why it's not, I don't know. But I don't know. So this is something that you definitely want to commit to memory. And you can actually test it. Take this, differentiate it with respect to R. And you'll get the magnitude. Oh, I erased it. You'll get Newton's law of universal gravitation, at least the magnitude part. Right. Differentiate the spring force equation. Spring potential energy is 1/2 kx squared. Differentiate that, and the negative derivative of that will be Hooke's law, negative k times x. Okay. Right, you can see that if you differentiate this, you just get k times x. If you do the negative derivative of it, you get negative k times x, which is Hooke's law. So anytime you differentiate a potential energy function, if that potential energy function is associated with a conservative force, then you'll get the value for that force, okay? Or an expression for that, the value of that force as a function of position, right? When you stretch or compress the spring, the force associated with how far you compress it is a function of the compression distance or extension distance.
So you just get G M1 into R over R squared.
Yeah.
Because that's the variable.
Yep. Because that's R to the -1, right? And then so if you differentiated just this, then you get GM1 N2 over R squared. And then the negative of that would be the scalar part of the potential energy, which is negative. This is weird. It's weird thinking of gravitational potential energy as being negative, but it's don't worry about that too much now, but we will do a much more thorough analysis of that at the end of the semester. That'll be the last thing we do. That and air resistance, that'll be our last thing before we jump into electromagnetism. I like pointing this out now, though, because this type of integral, E&M is more difficult. E&M is more conceptually difficult, mathematically more difficult than mechanics. And this, we start doing integrals like this, like right off the bat. Right when we get to electric fields, which is right at the beginning, we start doing stuff like that. So it's good to have seen it a little bit. Whether or not you're going to use this, you're probably not going to use it too much right now. But definitely when we do gravity at the end of the semester, And definitely when we get to electromagnetism, you'll be doing stuff like that a lot. And you will be using this on this current quest assignment for sure. Okay.